Good morning, everyone. Continuing from tomorrow, Professor Fu-Chun Zhang is going to give us his second seminar about Majorana zero mode and various topological superconducting system. And I forgot to mention one thing yesterday. Professor Fu-Chun Zhang actually was appointed as a APCTP distinguished professorship this year. So he was supposed to come to our center more often, but because of this pandemic, he cannot come to our center probably this year. But instead of physical visiting, he's giving us this series of lecture. And we hope he can visit us at least in near future, next year. Okay, so today he will give us his second talk. So let's welcome Professor Fu-Chun Zhang. Okay, please.
Okay, thank you, Professor Pang. And actually, I have planned to visit Korea, but because of this pandemic, so I have to delay my visit. Hopefully, my in-person visit will be possible next year. So let me share my screen first. Okay, so what I like to discuss with you is about Majorana zero mode in topological superconducting vortex. This has been an active field. I am personally involved in some of the theoretical studies. So this is the outline of my talk. I will give quite a long introduction because I assume some of the audience may not be familiar with this Majorana fermions and topological insulator and Majorana zero mode and its possible application in topological quantum computing. So after quite long introduction, I will focus on Majorana zero mode inside the vortex of topological superconductor. And then we'll discuss spin polarization dependent scanning tunneling microscope. Okay. And we'll present theoretical calculations compared with this experiment. So basically, I will focus on, after introduction, I will focus on one thing. I thought that probably is better than if I describe too many things. Okay, the other things I think are more technical. This led to our first discovery or first observation of Majorana zero mode inside the vortex core. And I will end my talk by making some comment, summary, and perspective. And these are my major collaborators. Because too many collaborators, I cannot list all of them. Okay. The first one, the left side, is Jingfeng Jia, and he is a professor in Shanghai Jiao Tong University who does experiment, and he is the main person who observed Majorana zero mode inside the vortex. And the second one is my former student, Longhui Hu, and he is currently a postdoc in Penn State. And my former colleague, who is currently in IOP, Chinese Academy of Sciences, Yi Zhou, and also worked together with Liang Fu in MIT. So first, let me just introduce what is called Majorana fermions. Majorana fermion, we call the Majorana fermion, actually was proposed by Majorana, young at the time, theorist, very broad theorist in 1937. So he found a real solution of the Dirac equation, which is different from the usual Dirac fermion we are using now, and actually it exists in nature, like electron protons. So that solution is different from Dirac fermions in the sense this solution is a particle and antiparticle the same. So that means this C equal to C delta, and this is a real. And mathematically, a Dirac fermion like A, which is a complex, may be split into two Majorana fermions. For instance, A can be written in terms of C1 plus IC2 delta. So A delta can be written in terms of C1 delta minus IC2. Okay. And the C1, C2 are Majorana fermions, which are real. And why you call them Majorana fermions? Because they obey usual Fermi statistics. Okay. And the C1, C, if you consider two different C's, different sides, they anti-commute each other. In the nature, in the particle physics, neutrino is a possible candidate for Majorana, but has not been confirmed yet. Recent activity or interest in Majorana fermion actually changed to the condensed matter physics. As we know that in particle physics, electrons antiparticle is a positron, and that is emitting MeV in energy difference. In condensed matter, such as in semiconductor, electrons antiparticle is the whole. The energy scale is EV or 10 to minus 3 EV. The other interesting point is in superconductor, elementary excitations is Bogoliubov quadriparticle, which is a linear combination of electron and a hole. For instance, like UA plus VA delta. I consider spinless, okay. Depending on spin singlet and triplet, the spin will be involved. In the spinless case, if U and V star, this emission conjugate, complex conjugate, then the antiparticle is particle itself. That's for Bogoliubov quadriparticle. So that happens when quadriparticle energy is zero. So we also call the Majorana zero mode. So that opens the possibility to observe Majorana zero mode in condensed matter systems. So there are two conditions. I think the second condition is possibly sufficient. You have electron and hole combination, okay? And the electron antiparticle or usual hole, the energy difference is small. Let me take a simple example of Majorana fermions. That is illustrated by Kitaev, who pioneered the field, is one of the pioneers. And if you consider a one-dimensional spinless P-wave superconductor, now the model is called the Kitaev chain. The Hamiltonian is simple, including the first term is the hopping, and its neighbor hopping term. And A here is just like a Dirac fermion, such as the electron. The second term is just chemical potential to control the number of fermions. The third term is the pairing. The pairing is neighboring pairing, AJ plus 1, and it's conjugate. So this model in the periodic boundary condition can be solved easily. Okay, but the interesting is to study this the possible this age state or end point. What that's interesting, and a topological new aspect. So that can be carried out by rewriting the Dirac fermion A equals to the two Majorana fermions C1 and C2, as illustrated in my previous slides. So after this, we found it's a Hamiltonian can be written in terms of Majorana fermions. You have C or C's. Okay, and there are two different phases. One is in the trivial regime. For instance, when chemical potential is within the gap, it's outside the gap, outside the band. Okay, and there's no Majorana aging mode. There's another interesting case, topological regime, where this there's two ends. You have Majorana aging mode. Okay, this is the cartoon. Okay, so that it's a cartoon way to illustrate how you generate Majorana fermions, starting from Dirac fermions, such as electrons. Okay, so you're rewriting a Dirac fermion in terms of two Majorana fermion. That is mathematics. But at the end, at the two ends of a Kitaev chain, there is a regime. The Majorana fermions were set at the two ends. So Kitaev proposed that about 20 years ago. Let me be more quantitative. Okay. So that one-dimensional system can be carried out by many ways. In particular, in any parameter regime, I think it can be carried out by renormalization group, DMRG, density matrix RG. So, but there's a special case when delta, the pairing, equal to the hopping T, that case. And this case can be studied analytically. Okay. So if I consider mu as a chemical potential, okay, in the Hamiltonian, then you can calculate the first excited state and the first excited state energy. Okay. Again, I consider non-impacting Kitaev chain. And give you some feeling. Okay, in the case mu, the chemical potential is less than T, and for find the length L is the number of sides on the chain, and that the first excited state energy can be calculated, which is this is positive because T is larger than mu, and this is mu to the power of L. So when L is infinity, this mu over 2T is smaller than 0, or smaller than 1. So that goes exponentially to 0 at the large long chain. So what about the wave function of this first excited state? What I plot here is this is the number sides, okay, and to 500, and this is the wave function. So you can see these are pretty much localized at the two ends. And note that this is the first excited state. Actually, if you consider infinity long chain, then actually you have twofold degeneracy, because the ground state And the first Excise state, actually the energy becomes degenerate. When the first Excise state energy goes to 0. And when L, the length, becomes finite, this split, okay, into the 2 state. And this is slightly below 0. This is slightly below above 0. So that state will be occupied. This upper level state will be empty. So we call the first Excise state. Okay. So Majorana zero mode, so-called Majorana zero mode, actually it's a kind of degeneracy in the long chain limit of this. If you split, you have 2. So in a sense, Majorana zero modes always come with pairs. Okay. And so that's the picture. And these, all the parameters can be analytically determined. Finally, of course, you plot numerically that wave function. So come back to the Kitav chain. The question is...
Yes, superconducting wala, eh? Actually, meron on.
Yes, any questions, or I hear some voice? Shall I continue? Okay. So it's natural to ask a question if the Kitav chain is stable, the Majorana zero mode and that model actually can be solved numerically. So what I plot here is a phase diagram. This is a chemical potential. This is the U. It's a unit of T. And here I consider T the hopping and the delta the pairing the same. Okay. So in this simple limited case, if U equal to 0, that case can be solved analytically. Okay. Yeah, there's some instability on the video. So let me see. Okay, so this is the phase diagram, and you can find it numerically. Okay, but the interesting point is there are some lines can be found the exact analytic solution. Okay.
Fu-Chun,
Yes.
you need to share your screen again. We cannot see your
Okay.
PowerPoint. Sorry, there was some disconnection.
I found some, yeah. You can hear my voice, right? Okay.
Yeah, we can hear your voice, but we cannot see your
Yes,
PowerPoint. No, in the middle, there is a share screen.
Yes,
Share screen.
yes. Okay, I found it. So can you see this? My
Yeah.
okay.
Make it slide.
Yes. So let's see.
Right.
I think that probably has been for a few these slides. Have you seen the slides before?
Yeah, I think you can start from this
Okay.
slide.
Okay. Yeah. Okay. So these slides is to show the Kitav chain. the solution for the KTF chain is stable against the interaction. Here we use the nearest neighbor interaction, which can be positive or negative. And what I draw in this figure is a phase diagram obtained numerically. Okay. And the interesting actually contribution is to provide analytical result for one line. That's the blue line at mu equals 0. That's the blue line. Okay. For arbitrary u over t. For the parameter t equal to delta. That's what we call the symmetric case in the symmetric limit. The dashed line is a special case for mu, the chemical potential equal to particular point of u and t. That was solved analytically by Katsura in Japan. Okay. And the interesting part of the blue line is that you can study phase transition. Okay. The Katsura solution is nice, but it's within all the topological phase. Okay. So most relevant to our case is this topologically phase, which gives you the two end point Majorana 0 mode. It's stable against the interaction, until the interaction is very large, equal to the bandwidth. So you may ask why Majorana particle.
Ask a question, Fu-Chun.
Yes.
The first question is, how did you treat this interaction U?
Yes.
Did you
The way, yeah, so the way to do, yeah, the interaction U here is the way you can solve is you rewrite on this is similar to what the KTF did. You rewrite on the Dirac fermion C in terms of Majorana fermions, like a Cj. Okay, here Cj equal to 2, like a gamma J1 plus I gamma J2.
Right.
And in that case, when you rerun on this, okay, in the symmetric point, you get this bilinear term. Okay. And then you do these two Jordan-Wigner transformation and the spin rotation, some mathematical technique, and which led to the exact solution. Okay.
I see. So you treat this interaction exactly.
Yes. This is this is exact solution. Like usual Jordan-Wigner transformation has been used. And also in the language of Majorana particle instead of Dirac particle.
And this, okay, then second question is, so this interaction U is not on-site repulsion, it's nearest,
Right.
Yeah. Then
Yeah.
how did you get mud insulator from this?
Well, that's not very, I will explain that. Okay. Why call the mud insulator? I think maybe charge density. Because this is spinless fermion, so every site you allow only one electron, or one Dirac electron, or no electron. So the on-site interaction here is impossible, just excluded. Okay. So we only have the nearest range interaction is U. It's the nearest neighbor interaction. And what we call the mud insulator, actually the referee later suggests we change the word to the charge density wave. Okay.
I see.
And so, yeah, so in that sense, charge density is more Prof.
All right, thank you.
Okay, so maybe I continue, okay. So the question is why Majorana particles are interesting, okay. And of course, from the basic science point of view, if elementary particle proposed but not found in nature, and you can find in condensed matter system as an emerging particle, of course, it has some interest from academic point of view. Here, I think the reason many people got interested in is because this Majorana zero mode is a potential building block for topological quantum computing. Because of quantum coherence, here it's protected theoretically by topology. And non-topological quantum computing has been developing very rapidly in the recent 5 or 10 years. And there are many proposals, including superconducting-based quantum computing, and also ion trap, and solid state. Basically, it's a spin up and down, okay. And among those, the superconducting-based quantum computing, or the based on Josephson junction, it's most, I think, attractive. It has been in the stage of showing the quantum supremacy. Okay, that means they have a few dozen qubits by Google, who is the leader, and also by IBM, Intel in the US, and probably other institutes, and also in China, including USTC and Zhejiang University, which I was there, and the Institute of Physics in China. So that is, I think, in newspaper, because it can solve some problems which the traditional computer cannot handle or hardly handle. The main issue for the non-topological quantum computing is the quantum correction. Okay, the quantum correction could need millions of qubits for universal quantum computer. For instance, one qubit, you need probably 100 or 1,000 to correct it, to make sure it is right because of the error in the sense. And topological quantum computing has, in principle, the advantage. It's you don't need any correction, theoretically. Of course, you'd avoid many other things like quantum poisoning. Then you may ask why these Majorana zero mode are related to this topological quantum computing. And to that, I myself not an expert on that, okay, but I just give you some flavor of that. Okay. So that is related to the braiding, okay. And by braiding here, we mean the way strands of wire or hair interlaced in a zigzag manner, okay. And they are topological distinguished braids, which cannot be transferred into each other without cutting the word line. This is word line, that's time, and this is space, okay. And first try of using physics, I think here to braid, to build a topological computer. Actually, it's on the quantum fraction quantum Hall effect. People observed 5½ quantum Hall effect and attributed it to non-abelian anyons. Okay, and Microsoft Station Q has paid a lot of attention on that. I think it has been over 10 years. Okay, so the idea about the non-abelian anyons is it's similar to anyon, but the pairwise exchange of non-abelian anyon leads to a unitary transformation of a matrix instead of a scalar phase vector. Suppose the 1/3 charge excitation in the fraction quantum Hall effect of 1/3 filling. That gives you 1/3 fractional statistics. That's abelian anyons. So when you exchange, you share a scalar phase. So non-abelian means you need just matrix. Okay, so in the simplest case, it's just the SU2 versus the U1. But the activity along that line, although interesting academically, I think has led on many interesting papers. Practically, it's not very encouraging because of the lower temperature and because not very uncertain about the 5.5 filling, the state and the age mode. Then I think after that, or during that period, people start to pay attention to Majorana zero mode. And it's a little tricky. Majorana zero mode, it's a Boglev quadriparticle. In terms of statistics, suppose I consider the occupation. Majorana zero mode, it's a special type of Boglev quadriparticle, so it obeys Fermion statistics. For instance, Majorana zero mode usually it's half occupied, half empty because it's a zero mode. So when we say Majorana zero mode plays a similar role as anion, non-abelian anion, I mean in the braiding. Okay. So first, I think I have this. Okay, this is actually it's I illustrated in my first one-chain problem. Okay, and I consider two Majorana zero mode. Okay, and you know, when you put them together, so this process is similar to you just you shorten the length of the Kitaev chain from infinite to a finite. So the energy of two Majorana zero mode will split. One is positive, slightly positive, the other is slightly negative. Okay. Then there are two cases. One is the lower level is occupied, and that corresponds to so-called even parity. Okay, that's the left side. The red dot indicates the occupied fermion. And the second case is the upper level is occupied. This is the first Excise state in my example of the Kitaev chain. Okay. That has order parity. Okay. So I have two possibilities when I move two Majorana zero mode together. That process we call the fusion. Okay. So you have two possibilities, plus and minus, in terms of parity. Then the magic is I consider 4 Majorana. Okay, if you want to qubit, you need at least 4 Majorana zero mode. Okay, so if I consider, I make these 1, 2, and 3, 4 as two pairs, as I draw here. Okay, this pair. Okay, this pair. I may prepare them. One is in the even. The second is odd. Okay. Then you just make this gamma 2, Majorana 2. Okay. Just moving around, braid around Majorana 3 and come back. Okay. And this process, you would think I don't change anything, come back. Okay. But actually, because it cuts, this branch cut. Okay. And because the vortex, actually, you have order parameter around each vortex, you have 2 pi phase. So when this moves around, you get a phase pi. So that change the gamma 2 to minus gamma 2, at the same time change gamma 3 to minus gamma 3. So at the end, after this braiding, the 1, 2 pair becomes odd, and the 3, 4 pair becomes even. Okay, so that process, it's similar to operation of a polymetric sigma x. Okay, you lower one and raise another one. So that gives you some idea of braiding of Majorana zero mode. And although there are a lot of proposals to do that, so far there's no experimental realization of the successful braiding on the Majorana. Okay. Now let me, to be a little bit more optimistic, positive, just show you some evidence of Majorana incandescent. And here is an incomplete summary. Okay, I think 90% effort have been in the past have been paid in the one-dimensional Y. Okay, and one-dimensional Y is a kind of a device to realize Kitaev chain. Kitaev chain says that I have spinless. Okay, but where you get the spinless? You get a spinless, you don't get a ferromagnetic. You need a superconductor there. Okay, so when the nano Y is to realize that objective. Okay, so in that system, actually, that was the first time to report zero by the peak, which they identified to be Majorana zero mode in 2012. Okay, and still it's the most well-studied system. And that system study has been led by Leo and Marcos, Charlie Marcos, two groups. Okay, they are in, for instance, Leo in the Deft and Microsoft. And the second interesting realization is in one-dimensional atomic ferromagnetic chain. That has been studied by Eli Yazdani in Princeton, reported the first one in 2014. And the third, I think, studied it's a superconducting topological vortex. Okay, inside the vortex, there are Majorana zero mode. So that is different from the 1D system in the previous two systems. Now it's 2D system. And this is most activities along this line actually in China, at least the experimental part, although theoretically I think it's in US, Europe, and Japan. I'm sure as I learned, there are some interesting activities in Korea to study topological matter. And that Majorana zero mode inside the vortex, the major person is Jingfeng Jia, okay, who carried out the experiment. I am his theoretical assistant to provide some input on the theory part. Okay, so that's how I am involved. And his experiment basically observed the two things. One is zero by the peak. The second is that Andrew refraction experiment, measure STM, found the spin polarization dependent. Okay. So later in the vortex core, by using STM, I think more direct evidence for the Majorana zero mode has been observed in topological high TC superconducting ion-based materials. That has been carried out by Hong Ding and Hong Jin Gao's group in IOP, and start to report in 2018. And I'm sure there are many others, okay, and some evidence, some controversial, but here it's just incomplete list. So let me just, before I discuss some detail, I present, just show you the present status of study on Majorana. Okay, And there are many evidence for zero mode, okay, in various systems. So that's encouraging. The most advanced system is nanowire, partly supported by Microsoft. Okay, very strong experiments group working on that. And observed what they see, it's actually the observed zero mode, okay. And the problem is some are Majorana zero mode, some are not, okay. If you do more careful study by purposely study disorder effect of that. For instance, Andrew bound state, which has almost zero energy. They call the quality Majorana, but actually they are not topologically protected, and probably not the good idea to use for topological quantum computing. And in the vortex core, the Majorana observed in various systems and in high TC ion-based superconductor in particular. The problem is in this high TC materials, the material quality is a big problem, not homogeneous, okay. And in the study I will show you by Jingfeng Jia, the problem is the mini gap is too small to distinguish. More serious or challenge is there's no gradient. It's even close at this point. Okay. So we are asking, of course, the question, although Majorana zero mode is encouraging for developing possible topological quantum computing, the question is the right Majorana, okay, for gradient. So that's, I think, $1 million question, okay, people are looking for.
I have a question.
Yes, please.
Yeah. So you mentioned that the so-called Andreev bound state is different from Majorana zero mode state.
Yes.
Theoretically, but actually, I have difficulties to distinguish these two things. So my question is, how do you distinguish these two bound state theoretically?
Well, I think they are stating Q. I have not worked on the problem. There are activities in stating Q. One person returned to Tsinghua University. He used studied disorder effect. And the response to the disorder for Majorana zero mode and Andreev bound state can be different.
Yeah, but
and his study says that 85% in Leo's experiment, it's probably not Majorana, okay, but about 15% of these zero mode are Majorana. So it's kind of not, I think maybe 2 years ago what they found.
Yeah, but my question is a theoretical question.
Yes.
Can we really differentiate between Majorana state and Andreev bound state?
Well, I think it's about whether it's topologically protected. That's the question.
I see. All right.
Yeah, it's based on energy. It's not either to distinguish. It just says whether it's topologically protected.
Right.
Okay.
I see.
Yeah, I'd be happy to discuss with you if you, since you are working on that, Andreev bound state. Okay.
I've been thinking about this for long. Okay.
Now let me just go to to discuss the Majorana zero mode inside topological superconducting vortex. Some experiment and some theory calculation, some detail. Okay. as I said, the reason we have possibly Majorana zero mode, okay, in the vortex of active superconductor, it's because I have a global quasi-particle, okay. And in the global quasi-particle, I have always paired negative and positive energy state. And in chiral P wave superconductor, okay, the vortex state actually cut-off chain is one dimension. In 2 dimension, I have possible chiral P wave superconductor, but the experimental confirmation actually it's a big question. Okay, the hope for material of strontium 2 luthenate 04 actually turned out to be not P wave superconductor, or has big challenge on that. So that was initially proposed by Reed and Green, okay, and by Volovic and by Ivanov. Okay. And but it's very difficult to realize that. So then a very interesting, important paper was given by Liang Fu and Charlie Kane in 2008. So what they propose, although you don't have chiral P wave, but you consider such kind of system. I have a topological insulate on the bottom and a thin film superconductor, say S wave, on the top. Then you add a vortex and magnetic field, okay, and that superconductor proximity factor on the topological insulate actually will lead to a similar effect as the chiral P wave. Okay, let me explain a little bit. Okay. So the superconductor, it's a proximity induced on the topological insulate. When I have topological insulator, I have a gap, okay, in the bulk. I have a surface, helical metal on the surface. That's the topological insulate on the top or bottom Fermi surface, okay. And we call the helical metal because here the momentum is locked to spin. For instance, this is the Fermi C, okay. Usually if I have Fermi C, every K point I have to spin up and down. Here I have only one spin. For instance, that the spin along, for the momentum along X direction, it's a point to the minus Y direction, okay? So spin momentum is locked. Here it's perpendicular. So that system, in that sense, is similar to spinless fermion as proposed by Kitaev or by Reed and Green, those people, okay? But there's an important difference. There's no time reversal symmetry broken in this system, okay? But for the purpose of inducing topological object like Majorana mode, this serves the purpose, okay? And so that was, if we, and Fu and King discussed this and found that there's a Majorana zero mode, okay, inside the gap on these systems, okay. So they don't need a chiral P wave, but they need a topological insulated surface, okay, with approximate S wave superconductor. That topological insulator on superconductor experiment was realized by Jingfeng Jia in Shanghai Jiao Tong University. And you just consider this upside down, and in experiment, okay, the bottom is SU superconductor, it's NB SE2. The top one it's a bismuth selenide, bismuth telluride. Okay, and they are the sample for, because they share the Se element, so they match pretty well. Okay, and the topology insulator they use, it's a few layers, say 5 layers. Okay, and if the proximity effect is large enough, then both the top layer and the bottom layer of topology insulator will be superconducting. Okay, so that is the case. If you have 2 thick layers, like 100 layers, but the top ones, you know, you don't see anything. Okay, just no proximity effect. And the bottom ones, although it's a it's proximate effect, the superconductor, but it's underneath, just it's between the superconductor and the topological insulator, and there's difficult to see it. Okay, here the top layer can be measured by STM. Okay. And the lower panel figure just shows, actually it's a real calculation by my friend Changhua Wang, okay, in Nanjing University, okay, for the 5 layers. And you see so-called Majorana zero mode is pretty much confined in the top, the 5th layer and the 1st layer. Okay, so that's the real calculations you can see. Then there's a issue about the detect Majorana zero mode and unusual refraction. There are many quasi-particle states inside the vortex close to the energy, okay, difficult to distinguish from Majorana zero mode. And that has been resolved by using the high TC material, which has a large mini gap due to the colorful quasi-particle. Okay. So the advantage is that there's unusual refraction, okay, as shown, proposed by Vicky Lau, Patrick Lee, and TKNG, probably earlier of 2010, okay, in study of nano Y. And they say that they show that unusual refraction depends on the wave function of Majorana and can be spin selective. Okay, so to detect this Majorana zero mode in the usual superconductor proximate topological interface, topological insulator, we need to use spin polarized STM. Okay, so that may measure local tunneling conductance. Okay, and that will have 2 parts. One is a normal part, which is proportional to local density of state. And that is the same for spin up and spin down, as I will show you later, okay, some detail, but this gives you some qualitative idea. The second part is unusual refraction part due to Majorana zero mode. And that only for spin polarization parallel to the Majorana spin or magnetic field. Okay, so total tunneling conductance you would expect to be spin dependent. That's the Planck proposal before he did an experiment. Of course, experiment was carried out mainly by his student, very bright student. Okay, and I think let me see. I don't have much time left. Okay, I will just skip a little bit about unusual refraction part. Okay, some detail. So this is the cartoon to show JAS experiment. Again, I have S-wave superconducting on the bottom and the topological insulator thin film on the top. And the experiment only can measure the top layer of the topological thin film. Okay, so what we show you here is the red one is just a spin polarization. Okay, and use ferromagnetic STM tip, okay. To STM, that's tip, okay, measure vortex core, there's a Majorana there. I use a spin polarized current, okay. So-called enrift is you have one electron in and one hole refracted, and a pair of Cooper pair that transmitted. That contribute to the tunneling conductance, okay. And the interesting part is the Majorana inside the vortex core, the spin wave function at the center, right center of vortex is completely polarized along the magnetic field, okay. So that tells you that if you apply different spin polarization, you will see different angular refraction, which contribute to the tunneling conductance. Okay. So that's some experiment, some detail about the tuning Fermi energy, which is important for experimentalists. Okay, and I will skip that. Okay, that's the experiment data for spin selective angular refraction. Okay, and that top left panel is just show a vortex. Okay, you can see the size of the vortex. Okay, and basically you have this red one's center vortex core. Okay, and to test first the student test. STM is a localized, so R, excuse me. The radio is about 10 nanometer away. Okay, so they found that this is, I consider fixed magnetic field up. Okay, and the ferromagnetic tip up and ferromagnetic tip down, basically there's no difference. That's STM, okay, experiment, which measures DI/dV, okay. And the lower panel is most important. And the left two figures in this panel that tells you about the magnetic field up case, okay. When the tip you use in the STM, the polarization is parallel to the magnetic field. You get a much larger signal, the red one, okay, than the black one. If I inverse the magnetic field, and that's the two right figures, okay, again, you find when the tip's magnetization is parallel to the magnetic field, the signal, I mean, conductance is larger, the red one, okay. And because this is only relative, okay, this is just the experimental result, the relative phase, compare this to that, for different magnetic field direction, it's meaningless. Only meaningful part is the comparison with the same magnetic field direction, with you flip the tip's magnetization. So that qualitatively shows that the spin plays important role, that should be come from the angular refracted Majorana zero mode. Okay. And before I go to some serious discussion, it's already 1 hour, sorry. Okay, we'll try to finish in 5 to 10 minutes. There are many series working on Majorana zero mode inside the vortex core. Here is also incomplete list of.
I have question.
Yes.
Can you go back to one slide?
Yes.
Yeah. First of all, you say you explained the upper panel data and the lower panel data different. then, but
Yes.
I don't see what makes this difference. Polarization is just same, but the only difference is
You mean, yeah, well, the top panel,
yeah,
top right panel
yeah.
is to show the STM result at the point 10 nanometer away from the center of the vortex.
Oh, I see.
The lower panel shows exactly the center of vortex. STM can be very accurate in that position.
Okay, then my question is the upper panel right-hand side. If you measure this STM little bit away from the vortex core,
Yes.
why did you see still this almost zero energy peak? You expect to observe this zero energy peak?
Oh, yeah, yes. Well, zero, the Majorana zero mode has a wave function. Spread is centered in the core center, but the spread in the lattice.
I see.
Yeah, I will show you some result in theoretically.
So that means still the upper panel is measuring Majorana zero mode.
Including Majorana zero mode. The tunneling conductance, as I, let's see. Huh? Okay, yeah, these slides, I said the STM measurement
Right.
measures local tunneling conductance consisting of two parts. One
Right.
is a normal part.
Right.
That is a proportional local density of state.
Mm.
That's the usual STM. Okay.
Mm.
There's another enriched reflection part due to Majorana.
Mm.
Okay. The second part is strongly spin dependent, polarization dependent.
So what you are saying is that the upper panel, right-hand side, is mainly measuring normal part?
Measure local part, and also even Majorana zero mode away from the vortex core.
Yeah,
The spin dependent, it's complicated. It's not a spin polarized.
I see. So
There are
that,
two facts.
right. So that's then my second question. So
Yes.
in this experiment, you assume the Majorana zero mode is at least at the center of vortex. Majorana zero mode has mainly spin polarized.
Yes, I will show you. It's a spin completely polarized at the center of the core, the vortex core, theoretically.
Is it because of this external magnetic field, or it's just
Yes.
yes?
Yeah, it's always parallel to the magnetic field.
I see.
Of course, he did the experiment after the theoretical input. Okay, but what I show you here is just the experiment first.
I see.
And you see, if you don't know any theory, then you will see it's polarization dependent. That's the fact, right? Yeah.
Okay.
Yeah, I will show you some result, numerical theoretical result. Okay.
All right.
Okay, let me just come to some technical detail. Okay, so we want to study vortex in topological superconductor. Okay, and that is related to surface of topological insulator, which is described by a helical metal, or just like the Rashba spin orbit coupling plus pairing. Okay, and to make the calculation, I think, more accessible, we consider a spherical surface. Okay, the reason is it's a closed surface. I have vortex. Okay, I have anti-vortex. In one calculation, I found two, Majorana zero mode. Okay. And so that the Hamiltonian is simple, can be written in terms of two parts. The first part is just describe the spin up the coupling term. There's no other kinetic energy, okay, on the surface of topological insulator. The second part is the pairing, okay, and this theta, delta theta, it's theta dependent because I have this spherical, it's basically distance. Theta is a distance, okay, from the center of the vortex. And the phi is the phase, describe a vortex, okay. And in this right panel, I show you, it's the eigen energy. You solve this problem, it's a single particle problem, okay, you can solve. And these are the continuous limit because of final size, I have discrete, okay. The red ones, red circles are in gap bound state, okay. And this is in terms of angular momentum when you solve these problems. So you find that there's one Majorana zero mode, okay, at m equals 0, okay. With a very, very high precision when a student carries out that. And the interesting part is about the wave function. What I show you here is Majorana and the first Excise state, okay. And this is Majorana zero mode. I have because I have both spin up and down, so the mode general can be written in terms of U1 C delta, U2 C. Okay, that's spin up, and the same for spin down. But U1 V2 U2 V1 can be this. And if this quarter particle is equal to its anti-quarter particle, then the condition is U1 equal to V2, okay, and U2 equal to V1. And we indeed found that, okay. So we call this self-conjugated Majorana, okay. That's that one. And the interesting part is in this case, I consider this R versus Xi. This R is the radial, okay. Xi is the coherence length in the superconducting state. I have this, the blue ones is U2V1, okay, U2V1 spin down. At this zero energy at the right core of the vortex, the state, okay. So this is vanishing. And the only component is the spin up part. If I assume the magnetic field is up, okay. So this Majorana is a spin dependent in the R, but at R equals 0, it's really completely spin polarized this way, okay. So this is important. And you may ask length scale. Length scale is Xi, okay. Xi is coherence length. And you do STM measurement, this is a very, very small length scale compared to the Xi, okay. So you can do very accurately. And what this lower panel show is the first Excise state, okay. First Excise state has this at the 0, R equals 0, it's a V1, U2, V1 is non-zero. So this is a complete spin down, the first Excise state, okay. And you may ask many other states, and the simple algebra shows you that actually at R equals 0, only 2 cases non-zero. One is for Majorana, okay, the spin up. For the first Excise state, it's a spin down, okay. And all other state, because just high order in the spherical Bessel wave function, okay, mathematically, or it's 0. So for the simplest measurement, focusing on R equals 0, the right center of the core of the vortex, actually all others high energy excitations are irrelevant. Only you can focus on the Majorana zero mode and the first Excise state. Okay. So that tells us that in principle, Majorana zero mode is completely spin polarized. The first Excise state at R equals 0 is completely spin down polarization. But in that material, the minute gap between the first Excise state and the Majorana zero mode, the energy difference is very tiny. So that is much smaller than the energy resolution of the STM. So what you see is in the ideal case, you would have the left side panel show the difference. But if the resolution is poor, like in our current STM, what you see is the right side. Okay. So that's what I show is the density of state for spin up. Okay, essentially the same because the weight for the first Excise state and the Majorana zero mode are the same. So then the angular refraction part, I just show you the result. We can calculate. Okay, it's completely spin polarized. Okay, so we can combine the two contributions to the tunneling conductance. So that's what I show you again. This is the same as before, the Majorana fermion or Majorana zero mode and the first Excise state. Okay, and you can, this is up and down, it's the same. And this is for the angular tunneling. That's for the density of state. Okay. For angular tunneling, it's added together. Okay, so that I just makes the difference between the spin up and the spin down. So again, I think that the density of state contributed from spin up and spin down are essentially the same because of the first Excise state and Majorana zero mode energetically not distinguishable, but the angular refraction add only on the Majorana zero mode. Okay, so that's what the experiment see that. Of course, quantitative comparison, it's it's rough. Okay, so but experiment see like 7 or 10% difference. Okay. So let me briefly give a summary on the spin polarization of STM inside vortex core of Majorana. Okay, so experimentally observes the local tunneling conductance different for spin up and down at the vortex core, attributed to spin selective and beautiful refraction. Okay, and the normal part basically the same give you, but the spin polarization, okay, dependent STM only seen near R equals 0. And at weak magnetic field, that's the experimental result. The reason why you need a weak magnetic field, because at a higher magnetic field, vortices are nearby, and they actually becomes not really zero mode. Okay. So by this, we at the time claimed that we have used the spin polarization of STM, show strong evidence for the Majorana inside the vortex. Let me very quickly go through this recent development. And the recent development is on the Majorana zero mode in high temperature superconducting ion-based superconductor. Okay, then the data has advantage. The first Excise state and the Majorana zero mode can be distinguished in energy by STM because the gap is much larger. Okay, and the data has been carried out by a few groups. Actually, that was topological in ion-based superconductor was theoretically first predicted by two groups, okay, on the surface, on the one layer and on the bulk. And that's what the Hong Ding's experiment. And this I want to show you also Dong Lai Feng's group in Fudan. They observed in different material, but also ion-based superconducting vortex. Okay. And of course, that has advantage. The disadvantage of this ion-based superconductor is material quality is not satisfied because of inhomogeneity. Now, that's my last slides. Okay. And I like to mention that the condition for Majorana zero mode at the vortex end points, okay, actually may be relaxed for doped topological insulators, okay. And that was examined by Vishwanath and his group, okay. And it's actually should be characterized by topological phase transition of vortex line. And we did some follow-up work to study this vortex line phase transition for Dirac metal superconductor. And second, I like to summarize is introduce the Majorana particle and zero mode in condensed matter system in my talk, okay, and present the first observation of Majorana zero mode in vortex by spin polarized STM. Of course, the experiment was carried out by my experiment colleague, Jingfeng Zhang. Okay. And about the perspective, search of Majorana particle in condensed matter system, I think remains currently still academic. Okay, but we hope we will find the right particle, okay, to perform topological quantum computing. The examples of Majorana zero mode inside the vortex and Majorana zero mode at the end of nano Y may not be the final, result we will use, although they are currently more actively studied. One example I like to mention is this Majorana bound state, zero mode. They are bound, so it's difficult to use. And if a particle is mobile, delocalized, probably it's better to be used in transport measurement to carry out the purpose of quantum computing. But that's some study underway, okay. I'd like to thank all of you for your attention and excuse me for quite a long talk, okay, exceeding for 20 minutes. Thank you again.
All right, thank you very much for very interesting talk. So session is open for the question. So any questions from audience? Okay, I have a question. Then can you show again the last few slides about ion-based superconductor?
Yeah.
Possible topological.
Yes, the ion-based superconductor was discovered in 2008. And people did not pay attention to its possible topological nature. But actually, there are ion-based superconductor, it's a multiple band, multiple orbital, okay, materials, different from the high TC cuprate. So, so actually, as some theorists, I think this band calculation, which suggests that there's some band inversion, suggests the possible, suggests the possible topological nature of the ion-based superconductor. Okay. So what Hongding's group and his collaborators did two things. One is first they use APES, spin polarized APES, to show the surface state of ion-based topological superconductor. Okay, in the normal state are just helical metal. Spin is locked to the moment. Okay, because APES, spin polarized APES, can show that. So that's the first. And they did that in Japan. And by Shin, S-H-I-N, he has probably the best the laser, the APES technique. So that's important. The second is they did a STM measurement to see the zero bias peak. That's the first initial of these. Okay. And later they have observed, in addition to zero bias peak, they have observed other Bogoliubov quarter particle, trivial quarter particle state, which is separate from the zero bias peak.
Mm-hmm. So in this scenario, in order to make the surface state become topological superconductor, so first of all, the system create topological insulator inside some of the band. Then that part to create surface state. Then this surface state should have proximity effect with the bulk superconductor. Am I right?
You are right. Thank you for this quite important question. Okay, I didn't have time to explain that. And what I show you in Jingfeng Jia's experiment is I have S-wave superconductor, niobium selenide, diselenide on the bottom, and on top I use topological insulate. Okay, a few layers.
Yeah.
So these are from two different materials.
Right.
One is the superconductor, the other is topological insulate.
Yeah.
And in ion-based superconducting, the tricky part is it's a multi-band. Yeah. So you can think in that way. Some bands are superconductor, okay. Yeah. Some bands are topological insulate on the surface.
Right.
So it's kind of self-induced.
Yeah.
So another way to say it's the proximity effect is the band in the K space. Mm-hmm. Yeah. So you don't have to make them; it's there. Right. And of course, it's not every ion-based superconductor is topological, but there are a number of them. Right. At least they are reported in like 3 or 4 different materials. Yeah. What Hongding first discovered is on this ion selenide and telluride. So it's a half selenide and half telluride. Right. So it's kind of disordered on the surface. Mm-hmm. So that's maybe it's advantage, but if you want to use as device, will be disadvantage because it's in homogeneity. You know? Right. Yeah.
So then my question is that we all very well, I mean, we all know very well the bulk superconductivity of ion-based superconductor. Main pairing mechanism is S plus minus pairing state.
Yes.
If you assume proximity effect of this bulk superconductor to the surface topological state, then this surface topological state should choose either S plus or S minus. If
Yeah,
right?
yeah. I think that's also a very good question. Okay, and the proximity effect, I think we're combined it together. Here is I think the electron pocket dominate.
I see. I see.
But actually, you raised an interesting question. You know, how to make the proximity effect larger? Maybe along the line, you know, they can design something. Yeah.
I see. Okay, thank you. So, any other question from audience? I think they are hungry for lunch.
Yeah, it's 12 there. Yeah.
Okay, so let's end the talk by Professor Fu-Chun Zhang today and yesterday. He gave us two very interesting the recent result of he and his group. So let's thank Professor Fu-Chun Zhang again. Okay, so this is the end of this lecture series.